Good afternoon, everyone. Today I am going to explain the two types of isothermal work, the isothermal reversible work and the isothermal irreversible work. Before that, we should see the mathematical formulation of first law. Now, we have delta U equal to Q plus W. So, in this, delta U is your change in internal energy, Q is the total heat supplied or removed from the system, and W is the work done. Now, we are focusing on the work done, specifically the isothermal reversible and isothermal irreversible work. Now, we know general formulation of work for any process is W equal to minus of P external into delta V. Now, if you want to visualize this, we take our piston cylinder system. We take our piston cylinder system. This is isothermal. So, the temperature of the system has to be always constant. For isothermal process, you can take the example of a refrigerator in which no matter how hot or cold the food you put inside, the average temperature of the refrigerator always stays constant. So, it is an example of isothermal process. Now, P external into delta B. If you take this piston cylinder system and you apply an external pressure, now there is an internal pressure also. Now we are focusing on compression here. So if you want to compress means the volume of this chamber between the bottom of the cylinder and the lower layer of the piston, it starts getting reduced. For example, at time t equal to 1, 0, t equal to 0, it is the initial position A. And if I take some time, after a certain point of time, at t equal to let's say t1, the piston moves to this point B. So we can see there is a change in volume delta V. So this is the basic formulation of first law. Now in isothermal work, basic formulation of work, sorry. This is the basic formulation of work. In isothermal work, we have two types, isothermal reversible and isothermal irreversible. Now in isothermal reversible, the main point is the process is very slow. Now we are seeing there is a volume change. Now what if I do an infinitesimally small volume change, like really small? Now if I'm doing infinitesimally small volume change to reach the point from A to B, obviously I will take infinite time. So any process in which the external pressure is there and it takes infinite time for the process to be completed is called isothermal reversible work. Isothermal reversible work. Now, so again, for an infinitesimal volume change, you will have, according to this formulation, an infinitesimal work. So that will be equal to dW equal to minus P external into dV. Now, to make this very small change in volume, your external pressure should be greater than internal pressure by a very small value of pressure. So if you write it in this manner, P external is equal to P internal plus dP. But dP is a very small quantity of, infinitesimally small quantity of pressure. Now the external pressure is greater than internal pressure, as you can see from this formulation. Why? Because you are trying to compress, you are trying to reduce the pressure. So the external pressure, this has to be greater than the internal pressure, then only you can reduce. Example can be a syringe, medical syringe. You can see there is a fluid inside the syringe and you apply pressure and it compresses. The same thing happens here. Now dP is a very small quantity, it tends to 0. So I can write P external is almost same as P internal. Now let this be my equation 1, let this be my equation 2. Now we are considering the entity, the gas inside this chamber, to be an ideal gas, because that is the portion that we cover in our chapter. So if it is an ideal gas, then it will also follow ideal gas equation. So we can write for the internal pressure. Now this will contain a volume and there will be some n moles of gas. So we can write P internal into V is equal to number of moles of gas present into R into temperature of this piston cylinder system. So I can write P internal equal to nRT by V. Let this be equation 3. Now if we integrate our first equation, we will get a total work done. So we write total work done W total is equal to integration of dW equal to minus of P external into dV. Now limits will be by VA and VB. Okay. Now from the previous equation we had W equal to minus of P we had P external P internal into dV integration from VA to VB. Now we had another formulation for P internal, we use it. So we use minus of nRT by V dV from VA to VB. If we integrate it, we will get, and it will be minus of nRT ln of V VA VB. So it will be equal to, if you take log base 10, you have to multiply VB by VA. Now VB is your final volume and VA is your initial volume. So you can write so this is the work done in an isothermal reversible condition. Now this was the formulation that we got. W equal to 2.303 nRT log of VF by VA. Just the magnitude. Then if you do, for example, I want to plot this on a PV curve. So what I do is, my initial pressure volume is VA, initial pressure is PA. Now I am doing compression, so my volume has to reduce, so it will be VB, and since from Boyle's law pressure is inversely proportional to volume, my pressure will increase, it is PB. Now we are taking infinite steps in a isothermal reversible work, so we are taking infinite steps. Now if you join all these steps, we get a plot, and since the function is continuous, we can integrate it and get that value. So the area under this curve, this is basically your isothermal reversible work. Thank you.